So, in the last class, we saw that. So, we started off our discussion with the fact that the loss given default is nothing but 1 minus the recovery rate, right? And that it is a bimodal distribution. Now, when I talk about a loss given distribution having a bimodal distribution, there are two questions that comes out to me. The first question is that what is exactly a modal or what exactly is a bimodal distribution? That's number one. Number two, the next thing that comes out to me is that what exactly is the distribution? What do I mean by a distribution? What are the different kinds of a distribution that I'm expected to have? Now, broadly, what we could see is conceptually there are two broad kind of distributions. One of the distribution is an observed distribution. So the observed distribution is the distribution which we get to see from the uh, from the relative frequency of the data, from the relative frequency distribution. The next thing that you get to see over here is the the theoretical distribution which is obtained from mathematical functions like probability distributions. So, so basically what we did over the last class was we started our discussion with the relative frequency distribution. Right? For the relative frequency distribution, what we saw was the following. That given that x is a variable and that x has certain outcomes, like x1, x2, like this up to xn, let's say x has n values. Now each of these n values are nothing but n possible outcomes of this variable x, right? Let's say if n is 10, and it means that x takes 10 different values, which may be or may not be repetitive, right? On the other hand, so what we have is the frequency distribution f. Now f is so x1, so corresponding to x1, we have a frequency f1, x2 corresponding to that we have f2, xn corresponding to that we have fn, right? So basically, the frequency shows the number of times a particular outcome occurs. Now, if I add up all the total number of occurrences, I will get the occurrence of each of the variables. Then I will get the total number of occurrences. Then the next thing that I have over here would be Fi by n. So this, for defining a relative frequency distribution, the concept of this relative frequency Fi by n is actually very important. Now, the relative frequency defines the relative chances of an x1 to occur. Just remember, right? So now, when we talk about this relative frequency distribution, so the relative frequency gives us the chances of uh, outcome. So it gives you the likeliness that at x1 occurs, likeliness that an x2 occurs, likeliness that an xn occurs, and so on, right? So it is this relative frequency which is very important. Now, understanding this relative frequency also becomes important because it is with this relative frequency distribution or with the different types of the different ways to which the relative frequency distribution is The relative frequency distributed gives you your different kinds of distributions. So in the last class, we saw that broadly there are two types of distributions which we can kind of infer upon from from the relative frequency distribution by plotting a relative frequency distribution. So one of them is a symmetric distribution, and the other is a skewed distribution. Now, in mostly in risk domain, we get to see skewed distributions. Now, the question that comes out over here is, what is a skewed distribution? The word skewed comes from the word asymmetric. That is where a distribution is not symmetric. So basically, if you plot the relative frequency on the y-axis and the values on the x-axis, the corresponding distribution that you get to see is either concentrated at the left and asymmetric towards the right, or it is asymmetric towards the left and concentrated at the right. Now, if the asymmetry of the distribution is towards the right side, then we call it a right skewed distribution. Hence, we call it a left skewed distribution. Right? So, this is something that we need to understand. Now, the most interesting part of this distribution analysis is that the loss distribution of a bank itself is skewed in nature. So I'll just redraw a couple of the drawings over here. I'll just redraw a couple of the graphs that I have constructed in the last class. So last class there was certain issues with the mouse or with the surface on which I was running my mouse. So your graphs look out to be horrible. So I'll just redraw a part of this graph, especially this loss distribution graph. Okay, so let's start with this axis. So like in any distribution, right? So what we'll do is the dependent variable, the relative frequency will be on the y-axis, and over here I have y, right? So over here, what you have is within 0 to x, you have your loss. You have your loss series, and over here you have your relative frequency. You have your relative frequencies, and the distribution looks something like this. looks something like this. So this distribution is clearly a distribution which we call the right skewed distribution. So basically what I'm trying to say is that basically without fail, this distribution is a right skewed distribution. It's a right skewed distribution. So the question is that why am I saying that this distribution is a right skewed distribution? It is because the skewness or the asymmetry is towards the right side. So because I'm sitting over here, this side is my right side, right? So basically, because the asymmetry is at the right side, so it's a right-sided asymmetry. So it's a right-sided asymmetry. Now the question that comes out over here is that how do we define this asymmetry over here? Or if it's a loss distribution for the bank, how do I define it? I'll say that the lower value of the losses are more likely to occur, and in fact the observed concentration of the losses is towards the lower end losses, and hence what you have is a concentration towards the lower end values. Hence your mode of the distribution also occurs at the lower end, right at the lower end values, and hence your mode occurs at this point. So basically the small value of the losses are most likely to occur. These are the small loss percentages which we can hope to see. Okay, so this is the part that I'll call the modal loss. In an observed distribution, the modal loss is the loss which has the highest frequency. Right, so I have a modal loss over here. But the question that next comes out over here is the following. Now, after I have looked into the modal loss, the next thing that I also look into is the median loss. Where is the median loss in my system? The median loss in my system over here is the midpoint of this loss series. So it is somewhere here. So this is your median loss, right? For this distribution, one thing that you can clearly see is that the median lies to the right hand side of the modal loss. That is, the median losses are greater than the modal losses because the modal losses have occurred at a lower end value. So it clearly shows that in this particular portfolio, most of the losses are small exposure losses. So the losses that will happen is not very large. But so the majority of the losses which happen are small end or lower end values. So as I move from the modal loss to the median, right? Now From median, I move to the mean. Now the mean losses in this distribution happen somewhere around here. So the mean losses are even higher than the modal losses, right? This is the mean loss. But what you observe over here is that there is a substantial difference between the modal loss figures and the mean loss figure. This shows that there is some kind of uh, impact of some values which has drawn the mean value very far from the modal values, right? So we need to understand what is that part. So that part is the presence of certain extreme values in the form of tail end losses of the bank, which is this part, right? So these tail end losses are considered to be huge volumes of losses, right? So basically, if I talk about this, these are your tail end losses. Now, these tail end losses are very huge in nature or in terms of their exposures, but they have very small exposure, but they have very small probability of occurring. Right? So it's not that so so they have very low probability of occurring. It's not that they have already occurred, but their values are incorporated because we believe that the loss distribution of a bank can range from zero to infinity. It's multiple situations are looked into, multiple values or multiple cases are explored before you decide what is the range of the value of the bank's loss that you are supposed to take. So basically, the existence of tail end losses, like huge volumes of losses with lower basics, is what we call what we call the tail end losses. So these losses are such losses, which if they do occur, they can put the bank into trouble. That is, the bank can go into bankruptcy as well, or it may dissolve as well. So over here, it is the existence of these extreme values which makes this distribution right skewed, because the skewness or the asymmetry is towards the end of the curve, right? So basically, if you think about it, right? So if you think about it, so in this right-sided, so in this loss distribution, so in this particular loss distribution, the mean losses play a very critical part, right? And we, as modelers, are interesting or are interested in answering this mean loss. So this mean loss is your expected loss, and it is in this expected loss where you have your PD to PD, LGD, EAD playing a place, right? And it is this EL which is used as allowances for loans and lease losses, which is used for provisioning bad debts and so on. So this expected loss is used for ALLL. So for reserving allowances for loans and lease losses. You have A triple L, then you keep aside your provision for bad debts and so on, right? And it is for this EL that, or it is this expected loss, which is a function of the probability of default, about the loss given default, and the exposure of default, right? So this is a typical case of a asymmetric distribution. The distribution is a right skewed distribution, or as we also call a positively skewed distribution, because the asymmetry lies on the right hand side, right? Now, so one thing that we can clearly see over here is that these three basic statistical measures of the mean, median, and mode is very important in assessing the nature of a distribution. So because these three measures are so important, we will be taking them up respectively and we'll be trying to assess them, right? And how is it that this distribution can be identified to be symmetric in nature, or how is it that this distribution would age and so on, right? So these are the three measures which needs to be explored better for better understanding of the distributions. So before I move on, there is a question which I would take up, and from there we would take it up, right? Okay. Before I just take up the question, then guys, just give me a minute. I'll grab my bottle of water and I'll be back. Just give me a minute. Okay. So, so before I move on, I have a question from Kiran which I'll take up and then I'll move on. It says that when a customer is defaulted, for how many months bank try to recover the amount from the customer and then decide to write off the loan amount. So, Kiran, this is totally kind of different basis on products to products, right? Now, I'll give you a very simple example for an unsecured loan product, right? So what I have seen is a typical recovery period is between 36 to 48 months, right? Now, if a bank can, or whatever the bank can cover between this time, they cover it. If what they cannot, they don't recover, right? So then it is given out to agencies. So that's a typical time which is taken. Like for you require at least 2 to 3 years, 2 to 4 years to cover a loan, depending on the principal, on the exposure that the loan had at the time when it was kind of the time when it defaulted, and then it was written off the books and collection has been issued. Right now, after the collection is done, then it's charged off from the books of the bank. So basically, a bank would held on to a recovery depending on its typical recovery cycle, its typical business experience. You cannot actually tell exactly pinpoint like what exactly is uh, the recovery time, right? So it depends on products to products, on historical experiences, and on a lot of other factors, right? But for a retail portfolio, a typical period is around 2 to 4 years. For mortgages, it's around 3 years, right? Or 2 years, something like that. So again, it depends on the type of the product and the time required by the business to start or initiate its recovery processes. Yes. So as Kiran says it, Seva says it, it is typically 36 to 48 months, right? Now, again, so there are a lot of other different business specific factors which determine the actual recovery period that a business will have, right? Fine, perfect. So, also one thing that we that I talked about looking over here is these three measures. But before I go into this part, right, so just let me reiterate the concept of a symmetric distribution and why is it that we need a symmetric distribution, right? So why is it that a symmetric distribution is is preferred over an asymmetric distribution in statistical modeling, and hence these transformations becomes necessary. So basically our objective is that if you have a continuous dependent variable and it is bimodal, it is not a unimodal distribution, right? So then in such a case, how do you ensure that? So if you have a bimodal distribution, first of all, what it means is that it is an asymmetric distribution. It is not a symmetric distribution because a symmetric distribution has a unique mode. So if you have a bimodal distribution, then there is a problem, right? Now, if you have a bimodal distribution, then that typically follows some other probability distributions, right? So that is something that we need to talk about. And when we are trying to say this, right, so over here, what you can see is there is a So one thing that we can clearly see over here is that there is a transformation. So basically, if the LGD distribution is a bimodal distribution, where one end is concentrated towards zero and the other towards one. So given that it has a bimodal distribution, therefore, working with this distribution like this becomes a bit of a challenging, or estimating the different factors which impact the loss given default, etc. is not possible using or without undertaking this bimodal variable through a transformation. So over here, the first question that we need to understand is two things. Number one, what is the importance of a symmetric distribution? Why do we need a symmetric distribution? So over here, first of all, let's start with the symmetric distribution in case. Now, the moment you have a symmetric distribution, the left hand side and the right hand side becomes very similar, right? If the left hand side and the right hand side is very similar, so what it means is the type of the observation which is there on the left hand side and the type of the observation which is there on the right hand side of the distribution is very homogeneous in nature, right? So, if an observation is homogeneous in nature, what it implies is that there are no outliers. So, one of the biggest advantages of having a symmetric distribution is that you know that there are no outliers to your data. Now, more than outlier, you know that the heterogeneity in your data is nearly zero. Okay, so when I talk about outliers, the entire idea over here is that the heterogeneity in the data tends to zero, right? The heterogeneity tends to zero, right? And now, what causes heterogeneity in a data? Heterogeneity in a data is caused by different types of categorical variables, by the interaction of different categorical variables, and so on, right? So over here, what you get to see is this heterogeneity which comes out over here generally is responsible because of the existence of categorical variables. Okay, the heterogeneity, as I said, is created by categorical variables. Now, in risk, we have a lot of categorical variables, right? And you take up any data set, you'll always see that yes, there are a lot of categorical variables factor variables involved over here, right? So, so how do you think can we reach to a symmetric distribution from an asymmetric distribution? So basically, if you think about it, what you will see is that a data set really contains a good variety of heterogeneity, right? And on the other hand, what happens over here is that when you want to get a symmetric distribution, so because of all these variables and multiple categorical variables, generally the distributions of the variables in a data set are not normal. So basically what we do is we generally create segments of homogeneous groups of loans such that the behaviors, the variables may behave in a symmetric manner. The distribution of the variables can be possibly symmetric. And that's where the symmetric distribution comes in, right? So basically the crux of the discussion over here is to capture each of these two types of distributions, right? So one thing that we would get to see over here is that so basically what we have previously seen is that if a distribution is of a so if the distribution of a of a portfolio is symmetric, right? So what it means is that these losses that you're looking into are short-run losses because the short-term losses that happen on a month-to-month basis, the portfolio booked accounts and all these losses. So so portfolio losses are normally distributed because they occur they occur over a period of time on a monthly basis, and every month it is not possible for them to display huge spikes and low spikes. Right. So, so over a period of time, the loss figures, the loss rates uh, in a banking portfolio is more or less symmetrically distributed. But when you change the definition of the loss to include both expected loss and unexpected loss, that is where the distribution becomes asymmetric because now you have two types of losses. One, those symmetric small volumes of losses which you have seen on a month-on-month basis the last 3 years, and then there you have a huge exposure which is your unexpected loss, both lumped in together. So even if you do have a mode which is capturing which over the lower end, so basically, the next thing that you need to understand is that there are also extreme values in the same distribution which is going to pull up your mean or your average values, right? So, so portfolio losses are mostly, those loss rates are more or less symmetrically distributed. So basically, if I look into the loss rates over a period of time, I'll get to see that they're more or less symmetrically distributed. On the other hand, when you look at the overall loss distribution and you bring in both the portfolio losses and the unexpected loss together, you get to see a greater variation and a positively skewed distribution, right? So, any questions up to this point? Students, are you clear about the fact that as to when a loss distribution can be symmetric and as to when a loss distribution can be asymmetric? Perfect. Okay, sorry, I was speaking on mute. Okay, so the next question that comes out is to talk about this bimodal distribution. So just let me talk about this bimodal distribution, and then again I'll come back to this symmetric distribution and identification of a symmetric distribution. How do you use mean, median, and mode to do this thing, right? So I'll come to that. So let's first talk about this bimodal distribution. Now, a bimodal distribution is a distribution with two modes, right? So when there are two modes to distribution, you know that it's a bimodal distribution. Now, when we talk about a bimodal distribution, right? So there is a So basically, for a bimodal distribution, right? Like LGD generally has a bimodal distribution because the concentration of it once happens at zero, and another big concentration happens at one, right? Okay, fine. Okay. So over here, now the first question that comes out over here is that, so there are two things, right? Now the first question that comes out here is that I have a theoretical distribution, right? Let's say I have an observed distribution which is bimodal in nature, right? So there are two modes. So one of the mode happens at zero and the other happens at one. Now the question that comes out here is the following: that why do I need to do a transformation and get it to a symmetric distribution for computing LGD? Now to compute LGD, so this is where this is where we need to sit back and we need to understand the modeling methods that we would use. So a very typical modeling method which is used in, uh, for modeling LGD is the regression models. Is the regression models. Now, even though the regression model, the family of the regression models is huge, right? We just to start off with, right? So one of the very simple pros that we have, so the regression model that we have is simple regression. Simple One of the very simple methodologies that we use to for predicting LGD is a simple linear regression model. And one of the basic assumption of a simple linear regression model is that the dependent variable has to be continuous in nature. So if your yi is not lying between minus infinity to plus infinity, he or she would not be able to develop the model. And they also require that the dependent variable preferably be symmetric. And if it's not symmetric, then it's suggested that the segments are made symmetric or symmetrically distributed segments are created, right? And then separate models be developed on that. So now before we go on to this, to link this concept of this assumption to the symmetric distribution and symmetric distribution to the bimodal distributed to the transformation, first we need to understand, have a basic understanding of what linear regression says or any regression model talks about. Any regression model simply tells you or tries to explore a causal relationship between the dependent variable yi, right, and xi. So it says that the dependent variable yi is a function of, okay. So what we try to do in the linear regression model framework is corresponding to every yi, right? We want to understand that which are the xi's which is influencing y the most, or what is the impact of xi on yi. And the question that we try to answer over here is, does x cause y? Right? So over here, what we are trying to assess is, we're trying to assess. Okay. So over here, what we have is an element of causality between xi and yi. So basically, when I'm trying to develop a linear regression model or any other regression model, what I'm trying to do is I'm trying to understand whether x causes y. So what I'm trying to do is I'm trying to understand what I'm trying to understand is that how is x causing y, right? So x's are called the independent variables and y's are the dependent variables. And one very important characteristic of regression models is that it puts a lot of assumptions, or it requires a set of assumptions to be satisfied, or necessary conditions to be satisfied when the model is being run. And two of them are, and two of the uh, the criteria on the dependent variable yi are: number one, that this yi has to be continuous, right? So you can see that this recovery process, this recovery variable is continuous in nature, right? And the next thing that we want to talk about over here is that it must be symmetric in nature as well. So the yi being symmetric clearly means that, right? The first part is it should be continuous, and the second part is that it must be symmetric in nature, right? So it has to be continuous and it has to be symmetric. Now, first, let's come to this continuous part. Now, the way linear regression actually works, or any such regression algorithm works, is that you have a set of continuous x's and you have a set of continuous y's, right? And regression equation is generally written something like this: that yi is equal to alpha hat, okay. So over here what I have is I have yi, and yi is predicted by alpha hat, which is the intercept, and beta hat, which is nothing but the slope coefficient associated with xi, right? Now the mathematical form is not important. What I'm trying to show you is that there is a linear relationship between the x and the y's, and that is what matters, because alpha hat is continuous, beta hat is continuous, xi is continuous. Therefore, this yi also has to be continuous in nature. Now, how do these figures come in? How do we estimate them? Estimation problems. We'll come to that later. But first of all, this is the first explanation, right? That the dependent variable is going to be linear, and it is a linear combination predicted by alpha hat, beta hat, and so on, right? So the question that comes out is that this has to be uniform. And this is where the second part comes, that yi itself has been defined as a continuous, right? So in order to ensure that, now since LGD models have a continuous dependent variable, let's say recovery rate, right? So what we need to do over here is we need to first of all transform this distribution, this bimodal distribution, into a symmetric distribution using some possible techniques, right? So that is the reason why this transformation becomes important. The transformation becomes important because, one way you try to develop models, they develop LGD models, is through this part. So is through linear regression, right? Now, when you are doing this exercise, one of the very important things that you have over here is that yi, or this equation, the regression equation, is linear in nature, right? And that it is symmetric, and it is continuous in nature. So the yi is continuous, and hence whatever prediction you make is going to make it so symmetric, right? So that's one. The second part was we needed the variable to be made symmetric in nature, right? Now, given these two, the first thing that we are concerned over here is that in this LGD distribution, I get to see a bimodal distribution. How do I work with it? So the way to do this is to convert this dichotomy, this bimodal variable, into a variable where it is where the bimodality does not exist, right? So to ensure that the distribution is continuous and symmetric, right, this transformation exercise has to be done. So over here we'll talk about this model. This is called the transformation. Okay. The transformation. Now, when I talk of transformation, there are a lot of different ways to transform. Right? Okay. So, same as the question that does transformation comes on a data preparation step? Yes, Seva, it is after you have done your initial data preparation and you have reached the final state of your distribution. Now you are doing a data transformation to correct out the shape of the distribution, right? So that's where transformation comes in. And one of the very famous transformations which we generally talk about is the box Cox transformation. Is the box Cox transformation. Is the box Cox transformation, right? Okay, fine. So now let's try to understand what does this transformation does. So generally, in the industry, when we talk about transformations, we talk about very simple transformation like log transformations. We talk about polynomial transformation, but one very robust approach of transforming uh, asymmetric variable into values such that the values are symmetrically distributed above that variable. A box Cox transformation plays a very critical role, right? Okay, fine. So what we'll do next is we'll talk about the box Cox transformation, right? Okay. So before that, I'll just take a 5 minutes break, okay? And I'll just grab the morning tea and I'll just be back. Hey, hi guys, good morning. Okay, yeah, sorry, I'm back. Fine. So as we were talking about, so you're talking about the concept of a transformation, right? Basically, what I have over here is I get to see, uh, yeah. So what I get to see over here is that I have a bimodal distribution, right? Now, when I have a bimodal distribution, so when I have a bimodal distribution over here, right, I cannot, with a bimodal distribution, it is not possible for me to develop a model, right, or develop a regression model which requires my dependent variable to be continuous and symmetric in nature. So, what do? I need to do some kind of an adjustment, some kind of a transformation which will give me a continuous dependent variable. And that transformation is done using a box-Cox transformation. So there are also other transformations as well, but I'll start talking about with a box-Cox transformation. And what exactly is this transformation? Why do we need the transformation? And how is it that it would help me get this transformation, right? So that is what we will first start off with. Okay, okay, guys, am I audible? Can you hear me? Fine. Okay. So what are these transformations? So when I talk about transformations, what do I mean? What I mean is transformations, or like these transformation techniques are monotonic transformations, right? So these transformation techniques that I have over here are monotonic transformations. On monotonic transformation, right? And the method that they use to do this transformation are power functions. So now the next important step over here is to understand how to do a box-Cox transformation. And before we talk about a box-Cox transformation, we need to understand what exactly is a monotonic function, monotonic transformation, and what is a power function, right? So You can actually read about this box cost transformation and power transformations from Wikipedia itself. So I'll just give you the link. You can keep it at your end and read it, because one advantage, the only reason I am suggesting Wikipedia over here is because this is a very concise description of the content, right? So over here, this is a very useful. So basically, let's talk about monotonic transformations first. So what is a monotonic transformation? What does the word monotonic mean? So what is a monotonic transformation? Yes. So what does the word monotonic mean? You need not think about any technical term. You can just give me the normal term that we use every day. Mm-hmm. Okay, Seva? No. Okay. So don't we say these things like, life has become too monotonous. So I hate this monotonic life. So what do we mean when we are saying this? Routine, right? So that means the same thing. The same thing done over and over again and maintaining the same relationship. So similarly, in mathematics, a monotonic function means a function which follows a routine path. So basically, if I'm talking about a monotonic function, if I'm talking about a monotonic function, what I essentially mean is the monotonic function. What monotonic functions mean is that, let's say I have two values, x1 and I have a second value x2. such that x1 is greater than x2. So a function f, right? So if x1 is greater than x2, right, then a function f will be monotonic if the function of x1 is greater than the function of x2. So x2, and this should hold over all the values of x, right? Let's say x1 is greater than x2, x2 greater than x3, x3 greater than x4. Then the function of x1 should be greater than function of x2, function is greater than function of x3, and so on. Let's say I have a function like this: f of x is x square, right? So every time I put in a value of x, I will get a corresponding value of fx, right? So fx equals to x square is my function. Clear? Okay, this is a function. Let's say x1 is greater than x2. Let's say x1 is 1, x2 is 2. So given that is this function monotonically increasing, so fx over here will be, so f of 1 over here is 1. So similarly over here f of 2, right? So over here one thing you can see is that when 1 is greater than 2, f of 1 is, sorry, when 2 is greater than 1, f of 2 is also greater than f of 1. If 3 was greater than 2, then f of 3 would have been greater than f of 2. So the function monotonically keeps on increasing. So that is what we call a monotonically increasing function. However, if the relationship breaks at any stage, then it does not, however, remain a monotonically increasing function. But some of the basic functions in statistics and in mathematics have been so created such that you can have a proper and a clear understanding of monotonicity, right? So the first thing for any transformation is that these transformations have to be monotony. It cannot happen that at one point there is an increasing transformation done, then at another point there is a decreasing transformation done. No, it cannot happen that way. If it has to be made normal, the basic idea is that the transformation must be monotonic throughout. So whatever is applied at point A, right? If it is whatever overall behavior it shows, after it is point to applied point 100, you will also see a similar behavior, right? So the transformation of the data set has to be monotonic throughout, because whenever you are doing a transformation of the variables, there is always a rank ordering, there is always a, a relation relativity involved, right? So that cannot be destroyed. So this is the reason why these functions have to be monotonic throughout, right? So that's the first point of the box transformation. That these transformations have to be monotonic, and the ultimate objective of this transformation is to cover up. You know, the ultimate objective of this transformation is to finish off, or is to convert the distribution into a normal distribution, right? Okay. So let's take a pause here today. Tomorrow we'll start off with power functions. I don't want to start power functions now because I'll not be able to complete power functions. So we'll start off with power functions on Friday, right? We complete power functions and the transformation and the box transformation on Friday, right? Okay, and in the meanwhile, I'll share these recordings with you so that you can go to on Friday. I'll share the recording so that before you come back on Monday, you can do the sessions. Okay, great. So thank you guys. Let's catch up. And in India today we have Eid. So wish you all the very best for the festivities. Thank you. Bye bye.